Hi everyone, here's a second lecture for chapter 7. Okay, so we're going to start from here. So you are seeing the line spectrum of hydrogen. Why do we call this a line spectrum? Because we see lines in the hydrogen spectrum. If you remember from our previous lecture, we saw the visible spectrum, which is this one. Oops. Visible spectrum. Go back. Which is this one. You see here, that's the visible spectrum, and we can see all the colors in the rainbow, like the 7 colors. But if you look at the hydrogen spectrum, so here what you are seeing at the top is a gas discharge tube filled with hydrogen. Okay, when the hydrogen lamp is connected to the electric source, due to the current, hydrogen atoms will get excited, electrons get excited, and it's going to go to a higher excited state. But it's not going to stay there, it has to come back down into the lower excited state or the ground state. When it coming down, it emit line spectrum like you see in this diagram over here. Okay, so how many lines do we see? We see 1, 2, 3, 4. 4 lines, and the 4 lines are that you can see here, like a violet color or indigo, and then you have 2 blue lines, and then you have 1 red. So these are the 4 lines that you can see in the hydrogen spectrum. And the continuous spectrum is what you are seeing here, which is the visible light, because it has the whole spectrum. Okay. And similar to hydrogen, if you look at mercury, mercury also has a line spectrum. And strontium, neon, and you take any element from the periodic table, they all have line spectrums, because these lines are due to emission of the light of the excited electrons. Okay, and they have different number of electrons, so the different elements have different line spectrums due to that. And this diagram over here shows you what are those lines that we saw for the hydrogen spectrum. Okay, so you can see here on the right side, you are seeing emission spectrum of hydrogen. Absorption is when it goes to high energy levels. The opposite of what you are seeing here is the absorption. Right now what we have in this diagram is the emission spectrum. And then you can see these purple lines. So this is the first level. We call it as the ground state. Ground state is first level. And then the rest are all excited states. When the excited electrons come to the ground state, which is n equals 1, so this is n equals 1 level, okay, n equals 1, that radiation occurs in the UV region. So that is why you see that as the ultraviolet region. And when the excited electron comes to n equals 2 level, that's when we start seeing these lines that we saw in the previous diagram. That is called a visible series. And how do you see this visible series and the lines? When excited electron, which is in the third level, 3 to 2, that emits in the red region, which is closer to the 700, right? And then another one coming from 4 to 2, and 5 to 2, and 6 to 2 over here, the visible series. Those are the lines that we had seen, and that also represent in the diagram to the left. So these ones right there, that's the visible series. And then you can consider this as your hydrogen atom, and the energy levels are associated in the circular pattern. So these are the energy levels. Okay, and then the hydrogen atom electrons also emit in the infrared region. The infrared region emits when the excited electron come to n equals 3 level. You see here n equals 3 level, this part right there. And that's what you are seeing here in the red region. That's the infrared series. So the excited hydrogen electrons emit in 3 different regions. When it comes to n equals 1, that's the UV region, which we cannot see. When the excited electron comes to n equals 2, that is going to be the visible series. That's why we see these lines. And when the excited electron comes to n equals 3 level, which is the infrared region, okay, that is the red ones over here, which we cannot see, okay. Spectral lines of atomic hydrogen. So the three regions that we talk about in the previous slide, you can also see it in this diagram as well. Ultraviolet series, and then we have the visible series, and then you have infrared series. If you want to find out the wavelength of these different transitions when the electrons are moving from one level to another one, we can use this Rydberg equation, which is 1 over lambda equals R 1 over n1 squared minus 1 over n2 squared. And R is a constant which we called as a Rydberg constant, and this is the constant that's given to you. For the visible series, remember the visible series is when excited electron comes to n equals 2 level. So if you are trying to find out wavelength for the visible series, your n1 going to be 2, and then n2 could be 3, 4, 5, meaning so you have these energy levels. N equals 2 is here, and this is 3, 4, 5, 6. So n1 is going to be then right there. N1 is going to be 2, like this. Okay. N1 going to be 2, and then N2 could be either 3, 4, 5, 6, and so on. Okay. So this observation led scientist Neil Bohr to model hydrogen atom, come up with a model for the hydrogen atom. So Bohr's atomic model postulated the following. The hydrogen atom has only certain energy levels, which Bohr called stationary states. So those energy levels that we saw, these lines, he called these as stationary states. Each state is associated with a fixed circular orbit of the electron around the nucleus. Like this. Remember, we saw these circular orbits like that. Okay. The higher the energy level, the further the orbital orbit is from the nucleus. So these are higher energy levels. If it is further away, meaning they are further the orbit, further the orbit is from the nucleus. Okay. When the hydrogen electron is in the first orbit, the atom is in its lowest energy state called the ground state. So if n equals 1 over here, that is going to be the ground state. And then the rest are going to be excited states. Atom does not radiate energy while in one of its stationary states. The atom changes to another stationary state only by absorbing or emitting a photon. Okay, so that means if the atom is one of these states, it would not emit radiation. If it is moving from one stationary state to another one, it needs to be done either by absorbing or emitting a photon of light. The energy of the photon, h nu, equals the difference between the energies of the two energy states. When the electron is in any orbit higher than n equals 1, the atom is in an excited state. So this is n equals 1, 2, 3, 4, 5, so on. If it is in n equals 1, that is the ground state. And then if it is in any one other than n equals 1, these are called excited states. Okay, excited states, right there. So this is a quantum staircase. So the stationary state is the bottom one, n equals 1. And then you have other stationary states, n equals 2, 3, 4, 5, and so on. So if you want to go higher up, you have to absorb energy going up, and coming down, you have to emit energy. Okay. This is the hydrogen spectrum lines which we had seen before. we talk about this one. And here's an analogy for the energy of a system. You can see there is a chemistry book on top of the desk, and the energy is 0. And when it comes to the flow, it has to lose energy, because remember, when it is at a higher place, what energy does it has? It has a potential energy. Now using the kinetic energy, it loses its energy and become now negative x. Okay. So the book cannot be in somewhere in between. It has to be either at the top or the ground state. Okay. So if you want to find out the energy of a system, we can use this equation right here. Delta E equals final energy minus initial energy. And the equation is negative 2.18 into 10 to the negative 18 joules, 1 over n final squared minus 1 over n initial squared. And 2.18 into 10 to the negative 18 is a constant. So if you want to find out energy of two different states, we can use this equation. Now let's put this into practice. A hydrogen atom absorbs a photon of UV light. Hydrogen atom, and it talks about a UV light. And its electron enters N equals 4 energy level. Calculate the change in energy of the atom and the wavelength of the absorbed photon. So we want to find out the energy, and also we need to find out the wavelength. Okay. So we can use this equation to find out the energy. Delta E equals negative 2.18 into 10 to the negative 18 joules. And then if you know the two different states, in final and initial, we can find out the delta E. Now you can see here, we are given N equals 4. And it is absorbing a photon of UV light. And it's a hydrogen atom. Remember, we talk about UV light is emitted when the excited photons or the excited electrons come to N equals 1 level. Remember? And then the visible light would be N equals 2, and infrared would be N equals 3. It says UV light, a hydrogen atom absorbs a photon, meaning it goes from N equals 1 to N equals 4, right? So N final then need to be 4 because it's absorption. How does the absorption happen? So you have here N equals 1 and then N equals 4 somewhere here. So it absorbs a photon of UV light. So the final going to be N equals 4, initial going to be N equals 1 because it is absorbing. So initial N equals 1, final N equals 4. So we can put that here. Same equation we use, to negative 2.18 into 10 to the negative 18. And then the final 1 over 4 squared, remember it need to be squared, minus initial 1 over 1 squared. Okay, so 1 over 4 squared. Let me do this calculation here. 1 over 16.0625.0625 minus 1. Right, this part right there in the bracket. So that will give you 0.9375. Okay, 0.9375. 0.9375. So this number you need to multiply by this number. You multiply these two together. So you can see here in this PowerPoint, it is not showing that you need to multiply with this number that you're going to get from here. So that's a typo. So you can do your calculation. Negative 2.18 into 10 to the negative 18, and you multiply that by this number. 2.18 into 10 to the negative 18. That will give you 2.04 with some other numbers into 10 to the negative 18. So this is negative, and the number you're going to get here also negative. So that negative and this negative will make it a positive number. And it makes sense because it's an absorption. Absorption is a positive number because it has more energy than where you started from. It is an absorption, which is again positive value. But if it is an emission, you would see energy would be negative because it loses energy. Okay, so that's how you calculate your delta E. We also want to find out the wavelength, and again here is a typo that it says 2 lambda, so you don't need this 2 part, it's just the lambda, okay, which is the wavelength. So we want to find out wavelength. So if you go back here, it is asking the wavelength of the absorbed photon. So remember, we can use this earlier. Remember, we did use this equation, energy equals h nu, and we know C equals lambda times nu. Excuse me. So we can write energy equals, instead of nu, now you can write excuse me, C over lambda, C over lambda for mu, and then you have h. I forgot to write h at the front. So you can rearrange these two together to find out energy equals hc over lambda. Okay, and if you are thinking about its difference in energy, you can just put delta right there. Okay, delta part, change in energy. So you can rearrange this again if you want to find out the wavelength. So then the wavelength would be hc over delta E. So that's what you are seeing over here. Lambda equals hc over delta E. Excuse me. Remember, there was a 2 here at the front of the lambda. That was a typo, so I removed it. And here you found the delta E. In this equation, you have energy. It's okay to convert it to delta E. So H is a Planck constant, 6.626 into 10 to the negative 34 joules second. And your C is the speed of light. And then you divide it by delta E, which you find from your calculation A. That will give you wavelength in meters. Once you get it to meters, you can convert it to nanometers using 10 to the negative 9 meters equals 1 meter. Okay, hope you get it. And this is an example of an emission spectrum. Emission spectra of strontium and copper. Remember, we did the flame test, and then we saw some beautiful colors. We saw orange for sodium, and then we saw violet for potassium, and we also saw red color for lithium. And those are all emission spectra of the metals. And here you are seeing strontium and copper. Copper is a beautiful blue-green, and then strontium is also red. Another example of emission spectrum is the fireworks. And for the fireworks, they use metal powder or a metal compound. So you can see it emits, it's emission spectrum of metals, different colors that you are seeing. Okay. And here's an absorption spectrum of sodium. Okay. So remember, we saw orange for sodium. That was your emission spectrum. So we only saw orange color like this. So what does that mean? All the rest of the colors sodium has absorbed. So the sodium absorption spectrum, it has absorbed everything but sodium, but yellow color. So yellow or orange color. So that's why we saw orange color right there. Okay. Okay, so we will stop our second part of chapter 7 here, and then I will meet you in this third one soon. Bye bye.